Number 31. What is machine learning optimization? How do you optimize a machine learning model? Why is optimization important in milliliter? Answer. Machine learning optimization is the process of iteratively improving the accuracy of a machine learning model, lowering the degree of error. Optimization is measured through a loss or cost function, which is typically a way of defining the difference between the predicted and actual value of data. Machine learning models aim to minimize this loss function, or lower the gap between prediction and reality of output data. Iterative optimization will mean that the machine learning model becomes more accurate at predicting an outcome or classifying data. To tune the model, we need hyperparameter optimization. By finding the optimal combination of their values, we can decrease the error and build the most accurate model. Tuning or optimizing hyperparameters allows the model to be adopted for specific use cases and with different datasets. The setting of hyperparameters happens prior to machine learning deployment. The techniques that you can use to optimize the hyperparameters of your model: exhaustive search, or brute force search, is the process of looking for the most optimal hyperparameters by checking whether each candidate is a good match. You perform the same thing when you forget the code for your bike's lock and try out all the possible options. In machine learning, we do the same thing, but the number of options is quite large, usually. The exhaustive search method is simple. For example, if you are working with a k-means algorithm, you will manually search for the right number of clusters. However, if there are hundreds and thousands of options that you have to consider, it becomes unbearably heavy and slow. This makes brute force search inefficient in the majority of real-life cases. Gradient descent is the most common algorithm for model optimization for minimizing the error. In order to perform gradient descent, you have to iterate over the training dataset while readjusting the model. Your goal is to minimize the cost function because it means you get the smallest possible error and improve the accuracy of the model. On the graph, you can see a graphical representation of how the gradient descent algorithm travels in the variable space. To get started, you need to take a random point on the graph and arbitrarily choose a direction. If you see that the error is getting larger, that means you chose the wrong direction. When you are not able to decrease the error anymore, the optimization is over and you have found a local minimum. In the following video, you will find a step-by-step explanation of how gradient descent works. Looks fine so far. However, classical gradient descent will not work well when there are a couple of local minimums. Finding your first minimum, you will simply stop searching because the algorithm only finds a local one. It is not made to find the global one. So you have to choose the learning rate very carefully. If done right, gradient descent becomes a computation efficient and rather quick method to optimize models. Genetic algorithms represent another approach to milliliter optimization. The principle that lays behind the logic of these algorithms is an attempt to apply the theory of evolution to machine learning. In the evolution theory, only those specimens get to survive and reproduce that have the best adaptation mechanisms. How do you know what specimens are and aren't the best in the case of machine learning models? Imagine you have a bunch of random algorithms at hand. This will be your population among multiple models with some predefined hyperparameters. Some are better adjusted than the others. Let's find them. First, you calculate the accuracy of each model. Then, you keep only those that worked out best. Now you can generate some descendants with similar hyperparameters to the best models to get a second generation of Models. You can see the logic behind this algorithm in this picture. We repeat this process many times and only the best models will survive at the end of the process. Genetic algorithms help to avoid being stuck at local minima, maxima. They are common in optimizing neural network models. Optimization sits at the very core of machine learning models, as algorithms are trained to perform a function in the most effective way. Machine learning models are used to predict the output of a function. Whether that's to classify an object or predict trends in data. The aim is to achieve the most effective model which can accurately map inputs to expected outputs. The process of optimization aims to lower the risk of errors or loss from these predictions, and improve the accuracy of a model. Machine learning models are often trained on local or offline datasets which are usually static. Optimization improves the accuracy of predictions and classifications, and minimizes error. Without the process of optimization, there would be no learning and development of algorithms. So the very premise of machine learning relies on a form of function optimization. The process of optimizing hyperparameters is vital to achieving an accurate model. The selection of the right model configurations have a direct impact on the accuracy of the model and its ability to achieve specific tasks. However, hyperparameter optimization can be a difficult task. It is important to get right, as over-optimized and under-optimized models are both at risk of failure. The wrong hyperparameters may cause either underfitting or overfitting within machine learning models. Overfitting is when a model is trained too closely to training data, meaning it is inflexible and inaccurate with new data. Machine learning models aim for a degree of generalization, to be useful in a dynamic environment with new datasets. Overfitting is a barrier to this and makes machine learning models inflexible. Underfitting a model means to poorly train a model, so it is ineffective with both training data and new data. Underfitted models will be inaccurate even with the training data, so will need to be further optimized before machine learning deployment. 2. Explain in detail machine learning techniques. Answer. Machine learning is a data analytics technique that teaches computers to do what comes naturally to humans and animals, learn from experience. Machine learning algorithms use computational methods to directly learn from data without relying on a predetermined equation as a model. Machine learning uses two techniques: supervised learning, which trains a model on known input and output data to predict future outputs, and unsupervised learning, which uses hidden patterns or internal structures in the input data. Supervised machine learning creates a model that makes predictions based on evidence in the presence of uncertainty. A supervised learning algorithm takes a known set of input data and known responses to the data output, and trains a model to generate reasonable predictions for the response to the new data. Use supervised learning if you have known data for the output you are trying to estimate. Supervised learning uses classification and regression techniques to develop machine learning models. Classification models classify the input data. Classification techniques predict discrete responses. For example, the email is genuine, or spam, or the tumor is cancerous or benign. Typical applications include medical imaging, speech recognition, and credit scoring. Use taxonomy if your data can be tagged, classified, or divided into specific groups or classes. For example, applications for handwriting recognition use classification to recognize letters and numbers. In image processing and computer vision, unsupervised pattern recognition techniques are used for object detection and image segmentation. Common Algorithms for performing classification include support vector machines, SVMs, boosted and bagged decision trees, k-nearest neighbors, naive Bayes, discriminant analysis, logistic regression, and neural networks. Regression techniques predict continuous responses, for example, changes in temperature or fluctuations in electricity demand. Typical applications include power load forecasting and algorithmic trading. If you are working with a data range or if the nature of your response is a real number, such as temperature or the time until a piece of equipment fails, use regression techniques. Common regression algorithms include linear, nonlinear models, regularization, stepwise regression, boosted and bagged decision trees, neural networks, and adaptive neuro-fuzzy learning. Using supervised learning to predict heart attacks. Physicians want to predict whether someone will have a heart attack within a year. They have data on previous patients, including age, weight, height, and blood pressure. They know if previous patients had had a heart attack within a year. So the problem is to combine existing data into a model that can predict whether a new person will have a heart attack within a year. Unsupervised learning detects hidden patterns or internal structures in unsupervised learning data. It is used to eliminate datasets containing input data without labeled responses. Clustering is a common unsupervised learning technique. It is used for exploratory data analysis to find hidden patterns and clusters in the data. Applications for cluster analysis include gene sequence analysis, market research, and commodity identification. For example, if a cell phone company wants to optimize the locations where they build towers, they can use machine learning to predict how many people their towers are based on. A phone can only talk to one tower at a time, so the team uses clustering algorithms to design the good placement of cell towers to optimize signal reception for their groups or groups of customers. Common algorithms for performing clustering are k-means and k-medoids, hierarchical clustering, Gaussian mixture models, hidden Markov models, self-organizing maps, fuzzy C-means clustering, and subtractive clustering. 10 methods are described and it is a foundation you can build on to improve your machine learning knowledge and skills. O regression, O classification, O clustering, O dimensionality reduction, O ensemble methods, O neural nets and deep learning, O transfer learning, O reinforcement learning, O natural language processing, O word embeddings. Let's differentiate between two general categories of machine learning: supervised and unsupervised. We apply supervised milliliter techniques when we have a piece of data that we want to predict or interpret. We use the previous and output data to predict the output based on the new input. 10 methods are described and it is a foundation you can build on to improve your machine learning knowledge and skills. O regression, O classification, O clustering, O dimensionality reduction, O ensemble methods, O neural nets and deep learning, O transfer learning, O reinforcement learning, O natural language processing, O word embeddings. 3. Explain in detail machine learning cycle. Machine learning life cycle involves 7 major steps, which are given below. O gathering data, O data preparation, O data wrangling, O analyze data, O train the model, O test the model, O deployment. In the complete life cycle process, to solve a problem, we create a machine learning system called model, and this model is created by providing training. But to train a model, we need data. Hence, life cycle starts by collecting data. 1. Gathering data. Data gathering is the first step of the machine learning life cycle. The goal of this step is to identify and obtain all data-related problems. In this step, we need to identify the different data sources, as data can be collected from various sources such as files, database, internet, or mobile devices. This step includes the below tasks: or identify various data sources, or collect data or integrate the data obtained from different sources. By performing the above task, we get a coherent set of data, also called as a dataset. It will be used in further steps. 2. Data preparation. After collecting the data, we need to prepare it for further steps. Data preparation is a step where we put our data into a suitable place and prepare it to use in our machine learning training. In this step, first, we put all data together, and then randomize the ordering of data. This step can be further divided into two processes. O. Data exploration. It is used to understand the nature of data that we have to work with. We need to understand the characteristics, format, and quality of data. A better understanding of data leads to an effective outcome. In this, we find correlations, general trends, and outliers. O. Data pre-processing. Now the next step is pre-processing of data for its analysis. 3. Data wrangling. Data wrangling is the process of cleaning and converting raw data into a usable format. It is the process of cleaning the data, selecting the variable to use, and transforming the data in a proper format to make it more suitable for analysis in the next step. It is one of the most important steps of the complete process. Cleaning of data is required to address the quality issues. 4. Data analysis. Now the cleaned and prepared data is passed on to the analysis step. This step involves O. Selection of analytical techniques, or building models, or review the result. The aim of this step is to build a machine learning model to analyze the data using various analytical techniques and review the outcome. It starts with the determination of the type of the problems, where we select the machine learning techniques such as classification, regression, cluster analysis, association, etc. Then build the model using prepared data, and evaluate the model. 5. Train model. Now the next step is to train the model. In this step we train our model to improve its performance for better outcome of the problem. We use datasets to train the model, using various machine learning algorithms. Training a model is required so that it can understand the various patterns, rules, and features. 6. Test model. Once our machine learning model has been trained on a given dataset, then we test the model. In this step, we check for the accuracy of our model by providing a test dataset to it. Testing the model determines the percentage accuracy of the model as per the requirement of project or problem. 7. Deployment. The last step of machine learning life cycle is deployment, where we deploy the model in the real world system. If the above prepared model is producing an accurate result as per our requirement with acceptable speed, then we deploy the model in the real system. But before deploying the project, we will check whether it is improving its performance using available data or not. The deployment phase is similar to making the final report for a project.